All righty, here's 2, 4, day 1. Let me get that written on here, right? Make sure these notes are nicely, whoops, that's not what I wanted. That's not going to give it a nice label. This will. Day 1. All right, really twofold in today's lesson. We're going to start to broaden up the discussion about function. I like to call them function families, categories of functions, if you will. We're going to start to see a few other possibilities that at some point we could work with, okay? Some of these will go into greater detail. You're going to notice today, not much, right? We're just kind of like, hey, here's what's out there, because really we're 2 months into this course and we've gone all in on linear functions and quadratics. And that's about all we've done, okay? There's more to come. So we'll take a look at those, have a brief discussion, and then we've talked about the piecewise function. I'm going to do a couple graphs of a piecewise function. One that's not too bad and one that's a little bit tougher, and we'll kind of finish with that. All right, 8 parent functions, okay? The constant, this is actually one we've seen. You know, some of these the book uses kind of a goofy name that I might switch a little bit. We've typically just called that a horizontal line, right? It's usually characterized by, you know, for this one, it looks like it's like y equals 0.2, okay? It's a line. It's not increasing or decreasing. This next one, it calls the identity function. Let's just call it linear, because here's the deal. Yeah, sure, it's y equals x, right? It's a line. M is 1. B, that's the slope, B is 0, right? If you wanted to change this to any line that you wanted, just mess with these two numbers, right? It's kind of saying that, oh, if the slope is 1 and the y-intercept is 0, it's a special line. We'll call it the identity function, whatever. That's like its own, it's the parent function for lines, which again, we have seen a ton of. Absolute value, we've worked with inequalities and done some algebra with absolute value. That's what its graph looks like. By the way, I'm going to go back up here and add one thing, okay? Because all of these are parent functions, so it's going to have, they're going to look pretty basic. Where we're going to go with some of these is we'll get into what's called transformations. Again, it typically means 3 things. Okay, if you wanted to change the graph, you're going to still stick with the basic shape, right? But you could reflect it, you could stretch it, and you could shift it, right? Now I'm gonna spare you the details from there, okay? But when we say transformations, those are really the 3 things that we're saying we could do to a parent function so that we could make a different graph so it perhaps fits the data that we have for a particular problem. All right, absolute value, right? It looks like a V. It's got a real distinct shape to it. So when we say, like, if we got into transformations of an absolute value, we could make the V wider, or we could make it skinnier, or we could move it side to side, up and down. Maybe we could reflect it so that the V opens, you know, down to something like that, okay? That's what we're talking about with transformations, but that's kind of a unique one. Absolute value looks real different from the others. Square root, okay? Really when we look at the square root function, right, we have to have one y value for each x. So if you were to say, like, hey, the square root of 4 is really plus or minus 2, there is like a whole other half to the graph down here that we ignore, okay? If we didn't, it would fail the vertical line test, and we say the square root operation isn't a function. So what you're going to find when we're talking about its graph and saying, hey, the square root function, we don't look at it, even though that's correct, right? The square root of 4 is 2 and negative 2. We would say, because we have to have just one answer, the square root of 4 is just 2, okay? And if we do application problems with the square root function, any data that would be modeled well by it, typically the negative answers aren't really relevant, okay? That's something to be aware of when you see those. All right, 4 down, 4 to go. All right, so the book calls it the squaring function, right? Whatever. Let's call it whatever you want to call it, which that's true. It's characterized by x to the second power, so it's squared. We all year have called it by what I would say is its real name, a quadratic, okay? I don't think there's a whole lot to say with those. I mean, we've worked hard for a while with making sure we're experts on quadratics, okay? Cubics, okay? Let's just say this, coming soon. That's probably one of the function families that we're going to look at pretty soon, okay? Notice here with a cubic, it has an x to the third power. A couple things to just kind of notice about it as we sort of look ahead to maybe working with those. To kind of contrast it from quadratics, those tails, they go in opposite directions. Here you can't really see it from the parent graph, but here's another thing that's going to come up. Cubics can change direction. You're like, hey, wait a minute. Why is that a big deal? Quadratics can change direction. Oh, wait for it. Boom. Twice, right? Cubic can change direction 2 times. Quadratics can only do it once. Okay? Good one to know. A lot of fun application problems that we could look at with cubics. It's a nice function family. Useful little function. I'm looking forward to that one. Reciprocal. Sometimes we call it rational. It's basically one function divided by another. Really the thing to see there for a little preview. Like right here, they have these vertical and horizontal lines where like the curve approaches but never touches. Those are called asymptotes. When you're dealing with a reciprocal function, or again, you might find me using the name rational, essentially one function divided by another, sort of. That's like more or less what they are. They're very much characterized by their asymptotes, right? If it's up and down, we'd say we have 2 different kinds. You've got vertical, and you've got horizontal. Okay? When we're working with those, a big part of them is identifying where those asymptotes are. Okay? Oh, the greatest integer function. We don't work with these a ton. Sometimes you'll see it called a step function. It's characterized by rounding down. You can see right here in this point on the graph, right there, all of those x values are less than 1, and you can see for their y value, they get rounded down to 0. We don't make the jump up to a y value of 1 until x is at least 1, if not bigger than that, right? That won't be a function we spend a ton of time on. It's a very unique graph. If you were using it in a word problem to represent some data, it'd be in a very specific situation, right? And that's not a bad way to view all these functions. As you see ones that get kind of weird, they're probably not as common, but there are certain situations where they would fit data and represent data really well. It's just not all that common. We've spent a lot of time on lines and quadratics. There's a lot of situations that get represented with lines and quadratics, right? And you're pretty safe to say that, like, if it's a function we spend a lot of time on, it probably has a lot of applications, right? Really broad ones. It could be in any kind of variety of context. The ones we don't spend as much time on, they're there, they have their place. They're just, if you're analyzing data, they're not going to come up as much, right? It doesn't mean they wouldn't. You'd find at like a certain time they do, but they just won't as much. All right, that was all 8 function families. The last piece here in these 2 slides is to take you through doing a graph of a piecewise function. Okay. Talked about this. It's a graph that has, well, I was going to say different. Here's a better word though, multiple. It has multiple domain restrictions, right? You can see it's got 2 different lines, one for when x is less than or equal to 1, one for when it's greater. The first thing you should do is take wherever the domain restrictions change, in this case 1, and with a vertical line, you should mark it. Because that now tells me I've got 2 graphs to make, and it's going to be split up on either side, okay? I'm going to make my graph the same way. Okay, I'm going to start with the first one where x is less than or equal to 1. Okay, so as always with a line, I start at a y-intercept of 3. I'm going to mark that. Now the slope is 2, so I go up 2 over 1, right? And notice right there, I hit the dashed line. I'm going to stop. I shouldn't go, because once I get past that line, I switch to the line negative x plus 1. Okay, so I can go over to the left because all this space is where this function goes. Anything less than or equal to 1. Okay. This part gets to be a little bit tricky too. What do I do at 1? Okay. Closed circle or open. This one should be closed because this is the function that we would use at 1. Okay, that's the function we would use at 1. So I made the line 2x plus 3, but instead of an arrow going to the right, once I got to the x value of 1, I stopped. I just stopped. Okay. It's time to switch over to the other one. Okay. Now I'm going to graph it the same way, right? Other than like taking the time to make a table, which I don't think you want to do. Let's stick to the same way that we graph a line. Okay. Start with the y-intercept. Now I'm just going to mark it lightly right here at 4 because that point's not a part of the graph. I'm just using it as a reference point to get this line graphed. Okay? I don't actually start drawing this line until I'm to the right of x equals 1. So now I'll go down 1 and over 1. These points are actually part of the graph. Okay? Now right here, this line at x equals 1, that needs to be open, right? Because then the rest of this line, this is all part of the graph, right? And it will approach 1. But remember, at x equals 1, I'm using this one, which is why it has the closed circle. The bottom one has the open, because the bottom one technically doesn't take over until x is bigger than 1. As soon as it's bigger, it takes over. Okay? A piecewise function with 2 separate lines. Okay? Domain and range down here wants us to look at that. For domain, as I look side to side, I don't see any breaks. Or anywhere that, if I looked up and down that x-axis, I don't see any place it doesn't touch the graph. Range, different story. Much different story, okay? Looks as though y needs to be less than or equal to 5. As soon as I go above 5 on the y-axis, I get to a big blank part of the graph. It doesn't go up there, okay? So it's not a part of the range. It's got to be less than 5, okay? Piecewise function with 2 lines. All right, let's up the stakes a little. Okay, this is about as tough as I'd get on you. 3, okay? Piecewise with 3, one of them's not linear. It's quadratic, okay? First things first, mark where the functions change. In this case, that would mean -2. Make sure that's really, like, actually draw a dashed vertical line on your graph, because I'm going to split this up into 3 parts. And then I'm going to go left to right. 1/2 x plus 5. I'm going to do that one first. That is for x values that are less than -2. All right, I'm still going to use my reference of the y-intercept. But again, I'm just going to draw it really light because at that point, it's not on the graph, right? It's the quadratic is the one I'm going to graph in the middle. So I go right at 5, and then I go down 1 over 2, and now I'm right on the border, okay? And I'm using a slope of 1/2, okay? I draw on my line here. I get to the boundary, right? It's always tricky. When you get to that, but do I include that point at the boundary or no? Include it or no? I'll just look right here. It does not include -2, big open circle. Now, if you're picky and you want to, remember I use this reference point at 5. If it's just a little dot, you could leave it there. If you want to go back and erase it, right? Technically, that point shouldn't be there. I was just using it to get started. -2 to 2, we have a quadratic, okay? Let's stick to the same plan for when we graph a quadratic. Let's figure out where the vertex is. B is 0. So -b over 2a is 0. If I plug in 0, I get -4, okay? So that's big. Now, the one challenge you might run into, okay? And I'm actually kind of rethinking how you may want to do this. What if the vertex isn't in our interval? Okay, that could come up now that I honestly think about it. Here's a backup, okay? Here's a backup option. Let's say the vertex, like here, this worked out fine because the vertex it's at x equals 0, which is between -2 and 2, so that worked out great. What if the vertex was like way over here, right? Because the quadratic is only getting graphed between the 2 blue lines. Here's a really simple way you can do it. It's a little tedious, but it's okay. Okay, it's between -2 and 2. Well, you could kind of go old school. And honestly, this might be a good time to go old school. Make a table. But I'd be very specific, right? For my x values. I would use -2, -1, 0, 1, and I'm going to be very careful with 2, right? Knowing that what kind of circle is going to go at 2. It's going to be an open, right? Because 2 is for the next line, -1/3, -1/3 plus 2. All right, so I already figured out this. I'm just kind of doing these quickly and plugging in the points, right? 0 and 0, okay? You wouldn't need to show any work with that table, right? It's kind of tedious enough to have to make it, but if you have a trickier function for that interval, that might be the way to do it, is just make a little table, because now I can see with this, all right, at -2, or right there. Right, and I had to be careful. Right there at 2, that circle needs to be open. And there's our quadratic that fits right in there, okay? All right, 1 to go, right? This is it's got a little more to it, right? This is the kind of the max case I think you should handle. Luckily, the last one's a line, so I'm going right back to, here's 2, right? Just mark that point real lightly. Down 1 over 3. That point I can mark a little darker because that point's going to stay because now I'm past 2. Down 1 over 3. And down 1 over 3, okay? Now as I connect these points, I gotta stop. This is kind of interesting. That's a closed circle because this includes 2. I'm kind of in between values, so I can't exactly see where I am. I think it's like 1.3, something like that. But that's okay. Your graph doesn't need to be that accurate, okay? It doesn't have to be quite that accurate. All right, to wrap up, let's talk domain and range. I'm looking side to side for any kind of breaks in the graph where a vertical line moving across the x-axis wouldn't touch. And I don't see it. I always tend to just write it out this way. I should have added this to the other one. You should know that if you want to say that means the same thing. Okay, better yet, here's the way you should write it. Because if I'm talking about the domain, I do want to reference that I'm talking about x values. So we'll go with interval. Interval notation, you could say that, right? It doesn't matter. Now we go vertically along the y-axis to check out what's going on with our range. Okay? Both of those arrows on the lines are going down, okay? And they would continue to go down. So there's no limit on how negative y could be. Again, I see like as I go up, there's some gaps, right, on the top part of the graph. It looks like y can't be bigger than 4, right? And there's an open circle there, so I'm not even including 4. I think y can approach the value of 4, but it's not going to get there, okay? It's not going to make it. Yeah, that's a good one to study off of because if you were asked on a checkpointer test to graph it piecewise, it's not going to be harder than that one, right? You have kind of a moderate difficulty one on the previous slide and one that's pretty tricky, okay? That's all for day 1. Day 2, so basically what I'm going to do in day 2 is I'll mess around a little bit more with some of the other function types, okay? The greatest integer function, square root, a couple of those that I showed you today. 2.5 is when we'll really get into transformations, okay, which will be a big important topic.